I've been talking, I don't know what's happening. Can you guys hear me? Can you guys hear me?
Yes, we can hear you now, sir.
Okay, thank you very much. All right, so yesterday the last thing we were talking about was the different procedures when it comes to building a model. Okay, is there any question? Anyone didn't understand this part? Is there anyone who didn't understand this part? Would like us to clarify anything? Anyone would like us to clarify? Any question? So all is well. Okay, so just to recap a bit here. So the first thing we will do is we're gonna do a data splitting. Between we divide the data into training sets, test sets, and validation sets. Remember, the validation set will work together with the training set. While you're training, you're validating the set, and then we can go to use the testing set to test the model itself. And then once we've divided the data, then we're going to use those data for data training, and then we're going to verify it, okay? And then we're going to test and then deploy it, okay? So, okay, so this is an example of supervised learning that shows how the learning phase happen. So in this case, we are trying to see if a certain player is a basketball player. Are we trying to do that? We want to let the algorithm learn from the data, and then it's going to give us an output, and the output can be yes or no. So this is a supervised. This is, I mean, it's a classification problem that we are trying to have here, because we will have two classes, a yes and a no class. And as you can see here, the first the first four samples here will be used as a training set, and then the last three will be used as a testing set. So this is a data splitting that we do. So we first do a data splitting here. Okay. So here we're going to use this classification model to predict whether a person is a basketball player under specific features. And what are the features? Can anybody tell us which features we're gonna use here to predict if the person is a basketball player? What are the features?
So they're using the name, city, and age.
Okay, so they're using the name, city, and age. Okay, but here the features now, a feature selection will get us to use the city and the age, right? And the name of the person. Those are the the features, and then we have the target has to be a yes or a no. So we will do to build this model. We've done a data splitting. So what the model now will do is it's going to learn. So in the predicting level, can you see here from this data that we have here? Let's go back here. Can you see these are the data that we have? We have Mike, Jerry, Brian, and then we will have for testing set, we're going to have this. So now when we create a model using this, right? We train the model using this data, and then we're going to test it using those data. So after we've used those, after we created the model, now we can bring new data. The new data that we bring, can you see these are the names of the people who were not there. The new data that we're going to bring do not have a label because this is what it's trying to predict now. So now when we take the new data, we put it into the model that we created. The application is going to be able to give us certain probabilities that will give us a probability of maybe the first one, Marine, to see if she's a basketball player. It gives us only 0.3, which means 30%. This one, 0.9. So you can see here, this one here with 0.9, that means 90%. So this person has been predicted to be a basketball player. So basically, we've used the previous data here to train the data, to train the model and test the model. Now we are using the model here with new data, and the model is now predicting. So that is what we call it. Can anybody tell us why is this this type of learning called supervised learning? Why is, in this example, we are talking about a supervised learning? Why are we talking about supervised learning in this case? Can anybody tell us why we're talking about the supervised learning? Why is it a supervised learning?
Because it uses level data.
Sorry? Why is it called a supervised learning?
The data is leveled.
Which data? Here, I don't have any data here. There's no level here with this data. Why is it supervised learning?
Because of the level data.
Yes, but I'm saying here, we don't have any level data. But why are we calling it a supervised learning?
I think so because we are pre-processing the logic, the thing that we are fixing, we are doing it again.
No. So what's happening here is this. This is the learning phase. This is when the AI was learning about how to predict using the name, the city, and the age, how to predict that a player is a basketball player. So this is the learning phase. So this is what, so this is what the person who created the system was doing to train the model. So here in the learning phase, during the learning phase, we created this model by teaching the machine with labeled data. This is the reason why we call it a supervised learning. Supervised learning has to do with the learning phase. Now we've already created the model. Now here we have the prediction phase. The prediction phase means now we are using this model in real life. We bring new data. This is what we're looking for. We want the AI to be able to predict this for this new data. And it's going to use the model that was created, apply to this data, and it can be able to give us the prediction. So the reason why it's called supervised learning, it's because during the learning phase, when it was learning about the data, we had labeled data. Yes. Okay. So how do we determine if we have a good model? To determine if you have a good model, there's a few things that we need to look at. The first thing we need to look at is a generalization capability. What is the generalization capability? Is how is the model reacting with data that it has never seen before? Can it accurately predict the actual service data? So basically, if you created your model, you use certain data. Now, when you bring new data that you've never used in the testing, you've never used in how to call it, in a training, data that you've never used in a training. Now, you can now see how is your model performing with those new data. So that's the generalization capability. Another thing is the interpretability. Is the prediction result easy to interpret? So if I have a scenario like this, there's prediction here. Remember here, guys, we had what? Yes and no. We said it's classification problem, right? Remember that. But can anybody tell us why, when we're using the model, it's giving us numbers? Not yes, not no. But we were solving a classification problem. Why do we have different numbers? Can anybody tell us what does it mean?
Because it's giving us the probability, 0 being no and 1 being yes.
Yes. So which means now the probability will determine. So we'll determine if it's above 5, we have a yes. If it's below 5, we have a no. Okay. So that's the thing. So the classification problem give you a probability. That's the result. Give you a probability which you will interpret into your yes or your no or your categories. Okay. So is the prediction result easy to interpret? What's the prediction speed? You can't try to apply a model on any AI tool and then it take forever to give you the result. So a good model needs to be faster. Okay, so the result needs to get to you faster. Okay, and then you have the practicability. Okay, so is the prediction rate still acceptable when the service volume increase? So if we increase the amount of data, we have this example here. In this case, we only bring 5 data in this sample. If you increase the amount of samples, is the model still behaving the same? Is it still giving you the results in a shorter time? Okay. So if you can confirm that, the model is a good model. Okay. Okay. So guys, there is a few things that we need to consider to validate the model. Remember, we first talked about a generalization capability. So the goal of machine learning is to make sure we obtain a certain model that is closer to the perfection. All right. It's not really about getting 100% of what we're looking for, but it's getting at least close to 100%. So whatever difference between the target value that we need to obtain and what we are obtaining is what we call an error. So the whole point of machine learning is creating algorithm and changing whatever we can change in order for us to reduce the error. Okay. So What is the error? The error will be the difference between the sample results predicted by the model and the actual sample results. That is called the error. So what type of error we have? We can have two types of errors. We can have an error that we get during the training. This is a training error. So an error that we get by playing with training data. It's called a training error. And then we can have a generalization error, which is an error that we obtain while we're using new samples on our model. So so the best model will have a very small generalization error. Okay, so now we're gonna have two problems. We're gonna call a problem of underfitting and overfitting. This comes as you're training your model. That's why we were saying you have to be careful with what type of data you are using, because sometimes you may end up having an overfitting model or underfitting. So when we talk about overfitting is when the algorithm does not fit the data well. What does it mean? It means that your algorithm is so advanced, but the type of data that you are dealing with are not really fitting the algorithm. We say your system is underfitting. So, no, sorry, I got it the other way around. That is overfitting. Underfitting is when your model or your algorithm does not fit the data. That means you have more data, but your model is not really being accurate. An example can be you have a facial recognition where you want to give a certain score for every feature. For example, the eyes of the person, the hair, the distance between the eyes, the mouth, and anything like that. But your system, your algorithm is only checking the nose and the lips. But you have more data to look at. But your model can only focus on the nose and the lips. So your model is underfitting. Okay, so overfitting will happen when we have your model, which is more advanced. It has to check for so many things, but what you really need is just a few things. So basically, in that case, we're going to have a training error of the model that is going to be very small because we are not dealing with a lot of data. But the generalization error will be large because now in real life, when you want to apply this, it's not going to work. So overfitting occurs when the training error of the model obtained after learning is small, but the generalization is large. Okay, so that is it. So this is an example of underfitting. So basically the model that you create is this one, for example. Because remember, guys, a model, what is a model? A model will be a formula. It's going to be a function. In mathematics, we call them function. So we're going to see an example here so you understand. So a model will be a function. So let's say this blue line represents a model. But look at the data that we use. So you can see that this blue line does not really fit this data here. So in this case, we have a underfitting problem. This is an example of a good fitting where the data, the model represents the data. But when you look at this, it's overfitting. You can see that the model is more than the data that it should learn from. So you have less data. Okay. So this is example of overfitting and the fitting end. Good. So remember now, the key now with machine learning will be to try and reduce the error. So the more we're reducing the error, the more our system is becoming accurate. So what can cause an overfitting problem? Remember, this is an error that we're trying to avoid. So the total error of the final prediction is calculated by using the bias squared plus variance plus irreducible error. So the only error that we will accept in machine learning is the irreducible error, but everything else needs to be adjusted. Okay, so generally what we have is that the prediction error can be divided into two types. We have error caused by the bias and error caused by the variance. Okay, so what is the variance and what is the bias? So the variance is just the difference between the prediction, the predicted result from the average value. So if we getting certain result, but when we train it more, we find other results, right? And then we can calculate the average value that we're getting. But now, the average value, that average value will determine how we're going to measure the variance. So the variance will be the offset of the prediction value result from the average value. Okay, so these can be errors that are caused by the model sensitivity to small fluctuation in the training set. So if there's a bit of changes in the training set, we can have those problems. An example I can give you is you dealing with data. That's why when we talk about deep learning, or as we continue about machine learning, we will talk about what we call the normalizers. Because when you're dealing with certain, an example can be you want to talk your features. You have the height of the person. You have the weight, and then you have the age. So as you can see, the height of this person, let's say we're calculating in centimeter, it can be 180. The weight will be, let's say, 79. And then the age of the person, let's say 23. As you can see, this number here, these numbers are completely different. Now, if we have to deal with thousands of data, calculations are not going to be done properly because of the difference, the big difference between these data here. So normalizers, what normalizers will do, we're going to look at, for example, the height. We bring a formula into this so that every height is converted into a value between 0 and 1. So maybe someone who's 1 meter, 180, it's gonna convert this value to 1.8, and and so on. And all the weights will be between 0 and 1. We do the same thing here, 0 and 1. And then here as well, 0 and 1. So that now all the values that we have are in between the same space. And this makes everything easy, and it makes our model accurate. Okay. So, and then we can have the error caused by the bias. So the bias is the difference between the expected or average prediction value and the correct value we are trying to predict. Okay, so a good model will be a model with a low bias and a low variance. And a poor model will be a model with a high bias and high variance. Okay, so now when we testing the model, it's very important for us to know when to stop testing, when to stop training. I mean, because sometimes when you're training, and then remember you are training and validating all your data and measuring the error. So now, as we are doing that, sometimes we get to a point where, as you are training, you have here, for example, you have a high variance and high bias and low variance. As you training, the model gets to a point where the loss is very minimal. Remember, this is the error, which can be called error or loss. Okay, so the error is also called a loss. So when we talk about loss in machine learning, we must know that's the error. We get to a certain point like this, for example, here. At this point, the training error is minimum and the testing error is also minimum. But if you continue training your model, now this error, testing error, starts increasing. So you went from a good model to a bad model. Why? Because you are training it maybe 1,000 times. Sometimes you realize that you can only train it maybe 100 times. So those are certain settings that we will need to readjust. So you need to understand now, there is different error formulas that are used to reduce the error. So it will depend as well on the scenario, on the problem you are solving. So if we're dealing with a regression problem, what is a regression problem? A problem where the output will be any value. It can be a number from 0 to 1,000,000 to anything. It's not a category. When we look at an issue like this, we have the MAE, the mean absolute error. Okay, so the mean absolute error formula, which is expressed here. So now, what we do is that this formula calculates the error. So we need to reduce this error to 0. That's the target. Because the closer this mean absolute error is to 0, the better the model can fit the training data. So we reduce that. This is how we create the mean square error, which is the formula that is going to be used. Okay, so in this case, remember, we need to, we are dealing with a regression problem. That means in our coding and everything, we're going to use the mean square error. But when in coding, you don't have to know this formula. We just have to specify it in our coding. And this is the formula that is applying in the background, but you won't have to write it. Okay, so let's look at a classification problem here. So when we have a classification problem, the way we will see if we have a good model, if the model is really performing well, we do what we call a confusion matrix. So a confusion matrix is something that will evaluate the performance of the model. So in this confusion matrix, you have the estimated amount or the estimated value that we wanted to get, and then we have the actual amount, which is the actual value. Okay. So if we have the actual amount, the estimated amount here, so if whatever information we have here, it's yes, that's what we need, and the model gets a yes, and the actual amount as well is yes, it means the model has predicted it right. So that's what we call a TP, or true positive. It was true and it was positively identified by the model. Something that is true, that's the actual value, and then it is estimated positively. This is the true positive. Okay. But if it's something that is not true, it's false, but it's estimated to be positive by the model, it's a false positive. So let's look at a real example. So now, by looking at this, we have all the false, we have a positive, negative, false positive, true negative, you understand? So by looking at that now, we can come up with formulas to calculate certain metrics that will determine if the model is good, that will determine if the model can be accepted or not. So we look at, for example, how do we calculate the accuracy? So the accuracy will be true positive plus true negative divided by positive plus negative. And then the error rate is also calculated like that, the precision, Now, when you're creating your model, now you can see what type of precision you need. What's the threshold of your precision? So looking at a real example, then you will understand it. So in this example here, when we're going to apply the confusing metric. So we have trained a machine learning model to identify whether the object in the image is a cat, right? So here we're trying to predict if the object in the image is a cat. So what we did is we use about 200 pictures to verify the model performance. Remember now, in this case, we are doing what? We are checking if the model is performing well. We've already, these 200 pictures are not the training set. These 200 pictures are being used to test the model. You understand, guys? So we want to check the performance of the model. So among the 200 images that we use, we have 170 images that are cats, and the others, which is 30, they are not cats. So that's the reality. So the reality is that we have 170 cats, and now we have 30. So that's the reality, which would give us 200 pictures of cats. So now when we look at this case, what we've done is that after checking the performance of this model, we've identified the result. We've identified that this model has predicted 160 images are cats, while the rest are not, which is 40. As you can see here, instead of predicting 70 and 30, our system predicted 160 and 40. As you can see, the difference that our system did. Okay, so now when we look at that now, remember now here, we have what? We have true positive, which means a cat that was identified as a cat. True positive. True positive, indicating the numbers of positive cases that are correctly classified by the classifier. So in our case here, what do we have? So the numbers of, on the picture that we have, the numbers of pictures of cats that were identified as cats by our system was 140. And the other cats, about 30 cats, which was not identified as cats. And then we have the false positive. False positive is numbers of pictures that were not cats, but they were identified as cats. There were 20. Okay, so now looking at this now, remember now these formulas where we can calculate the precision, we can calculate the accuracy of the model by using these formulas. Okay. So in this case, we can calculate the precision, which is true positive over true positive plus false positive. And then we can get a precision of 87.5%. And then we can also check the recall, the accuracy here. So the model has a 75% accuracy. Okay. Okay, other key machine learning method. Now, remember now, machine learning is all about learning from the data and reducing the error. The smaller the error, the better the model. So we have another method called the gradient descent. What is a gradient descent? It's just a method where we're using a gradient formula in order to reduce the error. Okay, so how does it work? It uses the negative gradient direction of the current position as the search direction, which is the steepest direction. So in this case now here, we're going to be looking, we see here, for example, the error is big, so we're going into the gradient direction until we can reduce the loss to its minimum value. Okay. Okay, do you understand that? But you'll understand more when we, as we're moving along. So there's many gradient descent formulas. It will depend on how you are training your data. We have type of gradient descent. We have the batch gradient descent. We have the stochastic gradient descent. And then we have the mini batch gradient descent. So what will be the difference? The difference is that when we're using a batch gradient descent, in this case, when we're using the batch gradient descent, we're going to have to use only certain samples. So we use the samples in total. So we use all the samples and we update the weight parameter. So what is the weight parameter? So here is what we have. Let's say we have, these are the features we're trying to determine someone's face. So we have, for example, here we have the eyes, the nose, and the lips. So whatever effects happen here, whatever the, if we will assign what we call a weight. So what's the value of these eyes to belong to this object? So it's gonna have a weight there. Each one will have its own weight. So now, if we dealing with batch gradient descent, it means we take the whole data set, all the samples in the data set, and we start updating this weight. We start changing this weight until we can get a good model. So we're now changing the weight at the same time for all the samples. But in a mini batch, in a stochastic gradient descent, what we'll do, we'll just randomly select a sample in a data set and update the weight parameter. So we're just going to update maybe for this one only and see how it's performing. So that is a stochastic gradient descent. And then the mini batch gradient descent, so we're basically going to be selecting certain groups of data, certain batch of data, and then we update the weight for those groups, and then we move forward. Okay. So just to summarize that, in the batch gradient descent, it's going to use all the training samples for training each time. The stochastic gradient descent will just use one training sample for training each time. And then the mini batch gradient descent will use certain numbers of training samples for training each time. So that's the difference. Okay, so we've learned we have gradient descent, which are methods used to reduce the error or the loss. And then we have what we call parameters and hyperparameters. Okay, so the parameters and hyperparameters are just settings that we're going to set as we training our model. So those settings will be how many times you want to train, how fast, how many amount of data you want to take, and all those settings that you can possibly think of. Those are parameters and hyperparameters. But the difference between parameters and hyperparameter is the person who is placing those settings or changing those settings. So hyperparameters are set manually. It means you as a developer, you set those settings. If you can change the settings manually, it's called an hyperparameter. But the parameters are automatically learned by the model. So the model itself will be changing the parameters. Okay. So when you think about parameters, think of hyperparameters. These, because they are set manually, this will be like a fire. You are basically changing the settings you want to increase or decrease or something like that. So in a model, we need to know that hyperparameters are just external settings. They are specified by you as a developer or the practitioner. Okay. So we can tune them. When we do deep learning, we're going to see how we will talk about neural network, how as a developer, you can choose how many layers of the network you want. So those are hyperparameters because you are setting those information. Okay. Some models that help you get the hyperparameters, you have, for example, the lasso ridge regression. We spoke about this yesterday when we were talking about the data feature selections. So feature selections to see how many features we're going to take and things like that. So we can set up parameters and set how many groups of features you want at the time. Okay, you have the learning rates for training in a neural network. So all those settings are hyperparameters because you are the one changing them. And when you learn about different type of algorithm, you will see we spoke about we will speak about a nearest neighbor, which is an algorithm. So the K in that algorithm is also an hyperparameter. Okay. All right, so now those hyperparameters, now remember that the hyperparameters are set by you as the practitioner, as you as a developer. Now that could be a problem because one person can choose a different setting from a different person. And when you change the settings, the performance increase. So how do you know what type of setting to set so that you get the perfect? So that's why we have other methods, other procedures that can help you search for the best setting. That's what we're going to do tomorrow. All right, guys, any question? Any question? Any question?